Hi, my name is Jim, and we're going to be talking about harmonics today. Not as the product of distortion, but from the standpoint of the signal components that make up common waveforms, and not so common also, but we're going to stick to common waveforms like square waves and rectangular pulses and triangle waves and things like that. So what we're going to do first off is take a look at a square wave, and this whole technique was determined by a mathematician named Fourier, and we're not building square waves with sine waves, but what we are doing is analyzing them, and every time you see a spectral spike, it is a sine wave. So for these common waveforms, fortunately, a lot of fairly complicated math is decomposed into relatively simple formula that we can use to determine the frequency and the amplitude of harmonics. So what we know here is we have a square wave that's 1000 Hertz, and it's going to sound differently than a sine wave of the same amplitude and the same frequency. Now the reason it sounds different is that it has different frequency components in it. Now if the waveform is symmetrical, we're only going to have odd harmonics. If it is asymmetrical, we can have even and odd harmonics. So why is this important to know this? And first off, and this is kind of a big deal because the FCC is involved in this, is that the harmonics, including the fundamental, called the first harmonic also, can cause interference. And even though we're dealing with 1K here, we have a component out there at 21K. Now let's pump this up, say, to 40 megahertz, and we have some really high frequency components. Now the thing is that if you have high frequencies, it requires a small antenna, a short piece of wire, to be effective. Now you might notice that your cell phone doesn't have an antenna protruding from it. And the reason is because the frequency is so high that a small antenna inside the cell phone is quite effective. So we may be radiating energy, even though we don't intend to, by having sharp edges and signals in the equipment we work on or design or repair. The FCC checks equipment, and if it passes their test, it's certified with an FCC Part 15 number. And it's kind of important to have that, because if you don't and you're manufacturing equipment, you can be fined. So the absolute worst thing that can happen is you interfere with the aircraft. So that is a big deal. Interference is quite important. Secondly is, what kind of bandwidth do we need to pass a rectangular waveform? And when I say rectangular waveform, think about a digital stream. Data coming out of a modem going into a computer, whatever. And third is that these harmonics called some kind of problem called inter-symbol interference, abbreviated ISI, where basically the ringtails associated with these from one pulse tend to interfere in the time slot of following pulses. So the receiver, who has to take all of this and convert it into ones and zeros, is more likely to make an error if we have significant ringtails or subsequent harmonics that can interfere with following pulses. So we're going to look at a common periodic waveform here, and we're going to start with a square wave, and there's nothing unique about this. It's a 50% duty cycle rectangular pulse. It's called a square wave because of the 50%. It's very common. It uses a lot of clock signals and things like that. And to determine what the duty cycle is, and this is where we're going to start here, 50% duty cycle, it's simply equal to the active time. And in these examples, I'm going to let the active time be the time high, abbreviated by tau, divided by the period. So if we wanted to analyze this waveform, and you've seen the V of t notation before, evaluating sine waves, this is a little bit more complicated because we have all those harmonics to deal with, but it's 2 times V and V is defined here. You have to be careful with this. And I put the dot there so it wouldn't be confused with 2 volts. So it's 2 times this value divided by 1 pi, and the 1 is a placeholder, times the sign of 1, again as a placeholder because we're dealing with the first harmonic, omega t plus. Now we're going to be dealing with the upper harmonics, 2 times V divided by 3 pi, sine of 3 omega t. That's how we know that it's the third harmonic. Plus the same deal with the 5th and the 7th and so forth. Now we can also write this in summation notation, and that looks like this: the sum of n equals odd, 2 times the voltage divided by n times pi, and n would be the harmonic of interest, sine of n omega t. So either way of expressing these represents the same thing. Now the dot 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 here means that this sequence goes on forever. And if we had a perfect sine wave, the fall time and rise time would be 0.0 seconds. It would be a mathematical discontinuity. It can't happen in the real world. And when I say rise and fall time, rise time would be the time it takes to go from 10% to 90%, and fall time would be the time it takes to go from 90% down to 10%. So these are going to be numbers that are greater than 0, which means that we're not going to have an infinite number of harmonics in a real world signal. Now, the way this is drawn here is you can kind of see that there's an equal portion above and below the 0 line here in the center. So the DC component of this particular signal is 0 volts. Now, if we come down and make it a unipolar pulse, which means it's only going in one direction, and again, I've defined V the same as I did here. The harmonic signature is going to be the exact same thing as we have here, except there's going to be a DC component. Now, the DC component's easy enough to find, and this is the general formula for any pulse waveform. It's simply V, this guy, times the duty cycle, tau over the period t, and for this it would be 0.5. Shouldn't say volts, 0.5, oh I didn't say volts, 0.5 V for a square wave. Okay, so we have no even harmonics, and if we go to solve V of t, and we plugged in all the values here, 2 pi ft for the first guy, I suppose it's 1 kilohertz square wave, so this would be 1,000, and then when we multiply this out, that would be 3,000 and 3 pi and so on and so forth. What we would end up with after doing that would be the instantaneous voltage at some point in time as specified here by t. Now, we really don't care. What we want to glean from this is the frequency of the harmonics and the amplitude of it. So the only thing we have to look at is the coefficient of the sine function and the frequency, which is the argument of the sine function. That's it. So it's going to be the amplitude, and this is going to contain information on the frequency. So Sinc function, S-I-N-C, is defined as the sine of x divided by x, and this allows us to determine the harmonic content or the signature of pulses with any duty cycle. So if you're working these, you have to have your calculator in radian mode. Very important. Nothing will work right if it's in degrees. So duty cycle is again defined as tau over capital T, and there's no units on this. If tau is in milliseconds, capital T has to be converted to milliseconds, so the units will divide out. And if you want to express that as a percent, which is usually what happens, is you just multiply that by 100%. So the limits on duty cycle are 0, there is no pulse, to 100%, which means it's high all the time. And that may sound familiar because that's basically the concept used in pulse width modulation. So, take a look at a harmonic content of a triangle wave, and it's a little bit different. It's riding on 0 volts. It is symmetrical, so we know that there's no even order harmonics. And we can kind of see that there's no DC component in this either. Now the equation for this is a little bit more involved. Again, look at your definition of V, and that's going to be 4 times V divided by 1, a placeholder, times pi quantity squared, times the cosine of placeholder 1 omega t, plus for the third harmonic, it's going to be 4 times V, this time divided by 3 times pi, cosine of 3 omega t, and so forth. So, once again, we really don't care too much about the instantaneous voltage, but what we do care about maybe is the amplitude and the frequency of the harmonics, which when added together will actually make a triangle wave. Now, of course, we don't construct them with a whole bunch of cosine waves. There are very easy ways to make triangle waves without using 1,000 cosine waves. So, getting back to Sinc again, let's take a look at something where we have a duty cycle other than 50%. So, what we're looking at here is the duty cycle again is defined as tau over t, where tau is going to be the active time, and I'm always showing that as being high here. It doesn't have to be. And the direct current component here is going to be, again, the duty cycle, expressed as a decimal, times V, the voltage. So what this would look like then is to find any harmonic V sub n would be 2 times V times the duty cycle times the sine of n pi tau over t, period t, divided by n pi tau over t. Now, this may look like a lot of buttons to punch in on a calculator, but realistically, after you get the first harmonic, all you need to do is multiply this by 3, and then take the sine of it, and multiply this by 3, and then take the sine of it. This is going to remain the same. So, subsequent calculations, if you're determining a series, aren't near as mathematically involved from the standpoint of entering numbers, and the possibility of making a mistake, of course, as calculating your first harmonic. So let's suppose that we have a 10% duty cycle pulse. Tau over t is 10%. And what we see if we look at the harmonic signature of this, now this blue line really doesn't exist. It's kind of the envelope of a sine of x over x waveform. What we'll see here is that we're going to get a null at the 10th harmonic, the 20th, and the 30th, which is simply 1 over the duty cycle. And what that means is that the harmonic at that frequency is an amplitude of 0. And you can also see is that we start with the first harmonic being relatively small and hit a peak, and then drop to 0 for our first lobe. Now what that's saying to us is that the first harmonic does not have to be the largest, as it is in the square wave. When we get over into here, this will produce a negative answer, and then positive answer, negative answer, and this here ringtail gets smaller and smaller in amplitude as frequency increases. Now, the narrower the pulse, the wider this is. The more harmonics, the more evenly they are in amplitude, and if we hit the limit on a pulse width of 0, the harmonics are all the same amplitude and extend out to infinity. Now, that's a mathematical concept, but that's where this would go. If we say made this 5%, we would get our first null here over at this frequency, and these here would be a lot closer to being the same amplitude than they are here. The square wave is the most easy to see, I think, of the rectangular pulses. So this is showing the sine of x over x, and when you work these on a calculator here, it'll give you an actual negative value for the second set of 10 harmonics and the fourth set, so forth, for duty cycle 10%. Now what does this look like on a spectrum analyzer? Well, spectrum analyzers work in quadrant 1. So what we would be seeing would be the shape with a null at 10F. Here would be the second lobe, only this time positive. Spectrum analyzer doesn't care about phase. Third lobe, and so forth. So everything's going to be going in the positive direction. Now let's take a look at some of the things that can happen here. And suppose we have a digital stream, and we're going to, say, modulate a carrier or something like that. And what happens now, as you can kind of see, is that these tails from this here are capable of interfering with the next pulse, or lack of pulse, could be a zero. So if we consider two pulses here, one being in blue and the other one being in red, as you can clearly see that the ringtails on the blue guy and the tails actually preceding it will sort of overlie some of the time for the red pulse, and likewise the red guy will be interfering with what the blue pulse is, and also with what follows the red. So this is a good example of inter-symbol interference. Now, we can help fix this because we want to keep the error rate in a digital transmission system to 0. Because if you're downloading, say, a file on the internet, if you get an errored packet, you have to tell the sender that you got it in error, and he has to resend the packet. So the remedy on this is we can filter this, and if we adjust this right, the second pulse can occur at the null point. Now, this isn't the best example to explain that, but that would be one of the things we want to do in the situation where we're dealing here with a 50% duty cycle waveform. The other thing we can do is there's a type of filtering called a raised cosine filter, and that has the ability to kind of squish the ringtails to attenuate them so they don't interfere with pulses adjacent to the pulse of interest. So if we look at this in the time domain, limited bandwidth, and just kind of made this up, but this is going to be the point where the receiver looks to see if it's a 1 or 0. Those are going to be the sample pulse points, and ideally that should be the center of the pulse. And what we see in blue, and this isn't very precise at all, is all kind of interference due to the ringtails of preceding and following pulses. So it's very easy for the receiver not to be able to pull off a 1 or a 0 as it was sent, and that constitutes an error, not good. So one of the ways we can use to take a look at pulses when they go through a transmission system, which is very popular, and this is in the time domain, and what we're going to use here is this waveform, and note that it's not a symmetrical 1-0 pattern. Now if we take our scope and analyze this and we mistrigger it, and what that simply means, it's going to be triggering on, say, a 1, and you're going to get an overlay of 1s and 0s. So a 1 pulse might look like this, and a 0 might look like this. And this is called a window. And what we want, and this is a perfect window, is something like that. A window, and the eye is completely open. So it would be very easy for a receiver to look at center of bit time, and relative to the center of the 0 and the 1 is determine if that's a logical 0 or a logical 1 pulse. So window's kind of telling us how good our system is. Now if we're dealing with limited bandwidth, all these edges, remembering that the edges of a rectangular pulse have to do with the high frequencies, are going to be sloped more. The rise and fall time is going to be extended. In addition to that, there's going to probably be some noise on the signal, and what you can see from this is that the eye is considerably closed compared to perfect. And that means is that the receiver, when he takes a look at this, doesn't have quite the comfort zone that he would with a perfect eye. So this is more likely, due to inter-symbol interference plus noise, to produce an error. So that's easy to do on a scope, is to see that. Now for an example here, sine of x over x, let's just take an arbitrary waveform that I made up. And what we're being told here is each horizontal mark is 15 microseconds. So I've labeled those 15, 30, 45, 60, and 75, and it's a good idea to do that. Not just to look at it and do it in your head, is write it down. You're less likely to make a mistake. The amplitude of this is going to be 6 volts. This is the active time high, tau, and then the period here is 75 microseconds. So the duty cycle, and DC is used in 3 different places commonly. One, of course, is direct current, the other is duty cycle, and the third on an oscilloscope would be direct coupled. So when you see DC, you have to put it into context depending upon what you're working on. So the duty cycle, tau over T, is 45 microseconds, that would be this guy here, divided by the period, which is 75 microseconds, which gives us a duty cycle of 0.6, and expressing that as a percentage, it would be 60%. Next, we can find the DC component of this, and since it's unipolar, we kind of see that it does have a DC component, and that's simply going to be the voltage times the duty cycle. 6 volts times 0.6 gives us 3.6 volts DC. That means if we took a true RMS meter and measured this voltage across a resistor or whatever, we would see 3.6 volts DC. So let's go about finding the first harmonic. So this is going to be 2 times, put him in there, the voltage V times the duty cycle, 0.6, times the sign in the numerator, 1, a placeholder, times pi times 0.6, the duty cycle, divided by 1 times pi times 0.6. Calculators in radian modes, and when we do that, we see we get 7.2 volts here times 0.951, and in the denominator we have 1.885 volts. And what that gives us for our first harmonic is 3.63 volts peak. So let's take a look at the fourth harmonic. Same deal here. I already have the 7.2, so I can just bring it down. And do note this. This is 1.885 here in the argument for the sine function. So all we would have to do with the fourth harmonic actually would be take this value and multiply it by 4. I haven't done that here. I've expanded it out, but there's not as much work here in number 4 as there was in number 1. And doing this here is what we get is 7.2 volts divided by 0.951, and then in the denominator we have 7.54, and then solving for that we end up with a fourth harmonic of 908 millivolts peak. So that'll conclude on this aspect of it. This is a very important subject, the sine of x over x and the Sinc function. It plays into every single thing having to do with digital communications, and this is kind of what lies under the hood of it. So thank you for watching.